In the previous section, we looked at the very basic equilibrium sums, how to do a sum of forces and a sum of moments. Now we will put this into a slightly more complex question to show you what to do when a moment is not directly obvious to see, and how can we take sum of forces smartly such that I can still solve my system. And at the end, I will solve a task that's slightly different, that's a bit more complex. First, let's take a look at this task 6 right here. Okay, here in task 6, we can see that we have a similar system to what we had in task 5, but with a different support here. So this is a 3-value support, which means when I remove it, such that I do my 3 cut, I need to have 3 supports that appear. I have my horizontal force, AH, my vertical force, AV, and I also have a moment now. Okay, so I will draw my moment in this direction. Okay, these directions right now we can say is arbitrary, but if you have an exam setting, please define them with the global coordinate system. Okay, so in this case, I'll draw it right here, just to say that I want my support directions to be the same as these two. So I have x, y, and if you guys have learned the right-hand rule, you will know the z direction is in this direction, and if you do your curl, it should be this direction that's defined as the positive z direction, which refers to my moment direction. Okay. Now that I've drawn this, I do again my equilibrium sum. So sum of forces horizontal is 0. Right side is positive. This gets me that AH is 0. No forces horizontally, so AH is directly 0. Now I can take the sum of forces vertically, because I only have one vertical unknown force, as 0. I'll take upwards as positive, just standard convention. Gets me AV minus F, right? AV is upwards, F is downwards. 0. AV is equal to F. Nice and simply. Now, let's do a sum of moments. Sum of moments at A. Okay. I want to take the moments at A because I have AH and AV, right? AH might be 0, but AV is not. And I don't want to include AV in my equation because it's more simple and I might have made a mistake up here. If I can avoid it in my equation, it's the most likely chance I get MA correct. Okay. So I will take my sum of moments at A because I know that AV doesn't have a lever arm on point A, such that it doesn't have a moment, it doesn't induce a moment on point A. Moment at A is 0. I will take clockwise as positive, just for fun. So I have F times the lever arm L, this distance. This is positive because F goes down, lever arm is this side, gives me a rotation like this. Okay, so F times L, positive, minus M, and just for your guys' sake, I will include the two A terms. AH times the lever arm of 0 plus AV times the lever arm of 0 is going to be 0, right? That means these two terms cancel, so M, let's add a subscript here, is equal to F times L. Okay, and here, just as a little exercise to prove my point, I will define this random point B over here. Okay, and this point B we'll say is in the middle of the rod, right at the middle. So this length is L half, and at some arbitrary distance A below it. Okay, complete unknown. And I will prove that the sum of moments at B here should get 0. So there will be a moment induced by AH, right? And AH, so let's define our sum of moments currently. And we'll define this side as positive, just so you guys kind of can remember what we're doing. Okay, so AH is going to be inducing a moment with this lever arm, right? AV also induces a moment with this lever arm, okay, the L half. And finally, our force F induces a moment with this lever arm L half. Okay, so let's include all three of these terms. And of course, also we have our point moment. I defined counterclockwise as positive this time just to show you that you can. Okay, so we have M positive. AH crosses this distance, that would be negative, right? So minus AH times A. AV goes upwards and then crosses this distance. It's this side, once again negative, minus AV times L half, right? And finally, the point force F. So point force F points downwards, crosses this direction. It is once again negative, minus F times L half. Okay, this term has to be 0. Okay, AH, as I said earlier, was 0, just from our force sum up here. AV times L half is not 0, so we have to include these terms. Now, M was F times L, right? Minus AV's magnitude, which was F times L half, minus F times L half. So this must be 0, right? This term clearly is equal to 0, right? So our moment sum does work. So that means we can take a moment, some location is arbitrary. Okay, very important. Now we will do a slightly different topic. It's going to be very similar as the question before, but it's to introduce something new. What I'm going to do now is known as a moment decomposition. Moment decomposition is basically when I have a point force and I want to take a moment at some point, but the force and that point are not perpendicular to each other. So here, this case is very simple. I have a force that's pointing at a 45-degree angle, okay? And I have the same question as before, so I know I want to take a moment at A, right? But in this case, of course, it's not too easy to decompose this because this force is not perpendicular. So how exactly do I take my moment at A to include this force? I will show you exactly how. Firstly, to get AH and AB. It's slightly different because I now have a horizontal component. So what I first have to do is decompose this square root of 2f into a horizontal and a vertical component, right? So square root of 2, I will draw a nice triangle. With this as a 45-degree angle, I know that this magnitude is square root of 2, which means this one is going to be square root of 2, let's say sine 45, this one is square root of 2 times sine 45, and this one is square root of 2 times cosine 45, right? Which both should just give me a magnitude of f. So this force decomposed is a f magnitude in this direction and f magnitude in this direction, okay? And if you're not sure which direction this is to draw, just follow this arrow, right? This arrow points in this direction, which is downwards and to the left. So the decomposed forces are downwards and to the left. With this, I can take my sum of horizontal forces as 0, right? I get AH minus square root of 2 of f times 1 over root 2, which is just this decomposition, right? So that would be just this term, is 0. AH is equal to f, okay? Which is exactly what you expect. Now, doing the same thing with the vertical forces. Sum of forces vertically is 0. Take upwards as positive. Here we took right side as positive. So AV minus square root of 2 of f times 1 over square root of 2 is 0. Then we get AV is equal to f. Now to decompose the moment, what I have to do is once again take a moment at A, but I have two choices of what to do with the square root of 2. Okay, so my first choice is to decompose the forces. So how I decompose the forces, I need to figure out a force that is perpendicular to my point A and one that's parallel to the point A, and I can say that just the perpendicular component generates or induces a moment at point A. So if I do this, the perpendicular component is of course vertical, and the parallel component is horizontal, so I would decompose it in these two directions, which gets me the same forces that I decomposed earlier, this one of magnitude f, and this one of magnitude f. Okay, this one of course doesn't induce a moment, and this one does. Sum of moments at A, we'll take this side as positive, is 0. F times L, which is this f, crossing this distance, which is L, right, this distance, minus m is going to be 0. So moment of A is equal to f times L. The second method, that sometimes is easier, I would say generally do this first method, but sometimes it's easier to actually find a still perpendicular distance of this force to the reference point. So to do this, what we have to do is just some simple trigonometry. So 45 degrees, we'll continue this line. This is still the 45-degree angle, same angle as before. And I need to get the perpendicular distance to my point A, just like before. So this angle is a right angle. So when I do this, I know that this length up here is L, right? We were given that. And that angle is 45, which means this angle is also 45. If I decompose this with Pythagoras or with basic trigonometry, I will get that this is L over square root of 2. This is L over square root of 2 as well. Okay. So sum of moments at A is 0, same direction defined as positive. I will get the magnitude of my force, square root of 2, times its lever arm, which is this length, L over square root of 2, minus MA is 0, which gets me that MA is equal to F times L. Square root of 2's cancel. And I end up with the same conclusion. Okay, nice and simple. Now let's put everything together and try to solve a different question type. So here in this question, we are given a cross like this, and we are given also a standard global coordinate system. And our job is to introduce a force N of a certain magnitude, direction, and position such that our cross is in equilibrium. So currently it's not in equilibrium. I have to add in some force, like this, for example, and this force has to cause this thing to go into equilibrium. So let's do this. Firstly, we'll do the forces sum, okay? The magnitude and direction have to be determined by the force sum, and the position is determined by a moment, right? Because there's only one magnitude and direction that can cancel out the forces. We have to do that first. Sum of forces horizontal is 0. Once again, we're going to take rightwards as positive. I suggest, honestly, just find a direction you're comfortable with and stick with it. I'll do rightwards. So the force we had to call n, so we have to do nx and ny. Nx to the right minus point force F is 0, so that gets us nx is equal to F. Now we do sum of forces vertically as 0, take upwards as positive, ny minus F is 0, which gets us ny is equal to F. Very, very simple. Now I know my force is magnitude F in this direction and magnitude F in this direction. Okay, so my net force has to be force in this direction, okay, that has magnitude F here and F here, which means it has magnitude of square root of 2F. So my moment balance now has to cause this to be in moment equilibrium. Now if we just look at this picture, this doesn't induce a moment, but this one does. This one induces a rotation in the counterclockwise direction, right? So I know that my point force has to be put somewhere such that it induces a clockwise rotation that cancels this out. Now, thing is, you can actually put this in infinite different locations, okay? It can be here, or maybe here, as long as the moment, actually this one's impossible, but as long as this can generate a moment that's big enough to cancel this force, you can place it technically anywhere, okay? So there's, in reality, infinite solutions. In order to make the thing more simple, what I will do is place it on one of the axes, such that only one of these force components generates a moment, okay? I will personally choose right now to put it on the x-axis, so since I'm putting it on the x-axis, my x force points into point A, such that the y force is the only one that's going to induce a moment, and I can just solve it with my y force. I'm going to put my force, say, here, okay? I'm going to put it obviously to the left, because I need my moment to be counterclockwise, okay? And now what I'm solving is the distance I have to put it from this point, which I will call Rx, okay? Let's call it Rx. So remember, this n has a vertical component of F. Finally, we have to do a sum of moments to determine the direction. So I will choose point A as my sum of moments point, and I will choose clockwise as the direction arbitrarily. I know that F is the only one that generates a moment on point A, since this F points into A. This is the only one that generates a moment, and this will generate a moment in the counterclockwise direction. So it's negative F times L plus ny times Rx is equal to 0. Rx being this arbitrary point. And then when I put my equation together, I get F times L divided by F, which tells me that Rx is equal to L. So if I put my Rx point, if I put my force on the x-axis, I have to put it at length L, such that this moment generated here cancels with this one, okay? And actually a very cool thing that you might be able to see as well is if I had taken my moment up here, this force points into it, and so does this force. That means this point up here has to have a sum of moments of 0, and the point forces F actually don't contribute to this at all. My equation will just have this. That means this has to generate a moment 0 also with respect to this point, which means this n actually has to point into it too. Given that this was a 45-degree angle, it has to be at position L, because this is also at position L. If you found this video useful, please like and subscribe to help the video reach more people trying to learn mechanics. If you want to support what I do further, consider also checking out my website where I provide many more exam-like questions that are much more difficult than what I can cover on YouTube. Every task there also contains a video explanation similar to this one. The website is constantly being updated to add more questions that you guys raise. If you want, you can also buy me a coffee on my Patreon with the link in the description of this video. Everything I produce here is done completely from scratch, so these videos take a really long time to make. Thank you.